near wall flow control flaps with pulse inlet velocity, and he's from Liberty University.
Thank you. Good evening. Like you said, I'm Ken. Dr. Strasser is my advisor. I'm a graduate student. I'm at Liberty University and studying near wall flow control flap. So just talking about our motivation, the problem we're trying to solve is flow separation. The solution could be shark skin. Our goal is to provide passive boundary layer control. So passive boundary layer control can be used aerodynamic and hydrodynamic ships, subs, race cars. We're going to be focusing on the aerodynamic, like airplanes. So you got an airfoil, of course, it's pitching up. You got stall happening. Looking closer there, you got flow reversal happening right on the surface here. We're trying to prevent that flow reversal so we can limit boundary layer separation. You guys know all this stuff, but effects of flow separation increase pressure drag, higher energy consumption, reduce maneuverability. So how can shark skin help? Well, there's tiny, called dermal denticles. They're little scales in the shark's skin on the order of 100 microns. This is a picture of one of them. And they will actually bristle up into the flow and prevent that backflow, and thereby preventing flow separation. And this angle has proven to be pretty important. So the scales with the largest bristling angles occur in this region on the shark. And if you look at it from the top, this region is behind the maximum thickness, and it's where high curvature occurs from swimming motions. So that's where we'd expect them to have the most flow separation control. So we suspect that the angle of the tentacle has a large effect. So this is some experimental work done by Santos. The color map is the fraction of time the flow is burst, so right at 50%, we'd expect flow separation. This is at a Reynolds number of 490,000. On the left, there's a flat plate. In the middle, it's a bursting angle of 30 degrees from the top of the shark, and the right is a bursting angle of 50 degrees from the flanks of the shark. So the higher bursting angles definitely mitigate flow separation. This is a higher Reynolds number and an even higher Reynolds number. So it helps to reduce flow separation at multiple different Reynolds numbers. So what are our methods in this research? We're going to discuss how we're going to simulate the experiment, and then we're going to discuss our moving mesh methods, and then we're going to discuss our proof of concept model. So previous studies, they're all experimental. They use PIV, they examine the large scale characteristics, they lack fine grained detail. So what we're going to be doing is looking at one tentacle and trying to model that computationally. So to get to DNS model flow over a bristling shark tentacle, we first of all need to validate our methods. Then we need to create a moving deforming mesh. Then we need to implement two-way coupled fluid structure interaction. And then we need to actually model and mesh the real tentacle geometry. So we're stuck in this stage right now. That's what this presentation is going to be about. We don't actually have the real tentacle on there, which is why we named it like a near wall flap. And we don't actually have the FSI implemented yet. So we're just focusing on getting the moving mesh up and running. So there's three options in ANSYS Fluid, which is the program we have to work with: smoothing, remeshing, and dynamic layering. The smoothing and remeshing option, in the smoothing method, the interior nodes absorb the motion of the boundary. There's no change in the number of nodes or connectivity, but it can't absorb large boundary displacements unless you pair it with remeshing, which agglomerates the badly skewed cells and remeshes them. But this is only available for tests. So you can see the remeshing like occurring like right here, and the smoothing right out here. So the other option is dynamic layering. So we're going to add or remove a cell layer right next to a moving boundary, but it's only available for prismatic elements. This is a 2D example of that. So this region has been just rigid motion prescribed by UDF. These regions are the dynamic layering zones. This then is a sliding mesh interface, and these are the moving boundaries. So comparing the two, dynamic layering allows you to use hexes, which are less numerically diffusive. It's less computationally expensive, but it does utilize sliding interfaces, which require interpolation, and so that could lead to errors. But it does maintain the quality of the mesh right near the tentacle surface itself, which smoothing and remeshing does not. So we put this in our proof of concept model in 3D. This is our inlet, symmetry planes, that's a top wall, and that's an outlet. That would be our tentacle, which is the new flap. This is a dimension to our domain, that's a velocity, so that gives us Reynolds number of 120, definitely laminar. These denticles occur in the, or they only are in the viscous sublayer of the flow, so they're all laminar anyways. So the mesh right next to the denticle moves with the denticle, but the mesh far away is just stationary. So that's where the sliding mesh interface occurs. We wanted to find out what effect that has on the flow. So in our results section, we wanted to find what that effect was, and we also did a kind of a side project on how pulse inlet feed would affect it. And then we just wanted to know, can we use dynamic layering for our full DNS FSI model? So these are our contour planes that I'm showing here. This is velocity contours. You can see a little distortion right here along the sliding interface. So to find what effect that had, we ran a steady state model so that we could get rid of the sliding mesh interfaces. And we took those two contours and we subtracted them to find the error. And so there's like a maximum of 5% error occurring right behind the denticle. This is a volume renderings right in the wake of the flap. That's where we see the most error. However, right near the denticle, there's like no error, and that means there's like almost no difference in drag with sliding interfaces versus without sliding interfaces. So that means that's not going to affect our solution very much, at least the drag portion. So then this is our transient model with the pulse inlet velocity. So on the x-axis, that's our inlet velocity, y-axis is our denticle cycles. And this is just moving sinusoidally, we're prescribing the motion. So our drag force is moving sinusoidally. Also, when we add in the inlet, pulsations, this is the legend is just the frequency of the inlet feed divided by the frequency of the denticle motion. So the denticle is moving 4 times every one pulse of the inlet velocity. So as expected, that's the drag. And then we have 2.5, 20. So you can see this kind of moves in a band here. So we decided to run it with an inlet velocity of 0.6 and 0.4, and we can see it nicely limits the band here. We're trying to see if there's any secondary effects or anything like that, but it's all behaving very as you would expect it to. So this is our average drag versus the inlet frequency. So at an inlet frequency of 1, right when the inlet frequency matches the denticle frequency, see a spike in drag, which is pretty expected. So we decided to phase shift this, and so the green is with 0 phase shift, and it's reaching the peak drag force right when the denticle is up, and reaching the minimum drag force right when the denticle is down. And like if you shift it 180 degrees or pi, the opposite occurs. It reaches the minimum when it's up and the maximum when it's down. So we put this on that same average drag plot that we had earlier, and as expected, for a phase shift of pi, you have definitely reduction in drag, but when it's in phase, you have drag increase. When it's out of phase, you have drag decrease. All what we expected to see. And then if we zoom in here, we also see 2 secondary spikes right at when the inlet frequency is twice what the denticle is, and when it's half what the denticle is. So we wanted to know what the effects of the sliding interfaces were, and we got that nice little plot there. And we also found that the drag difference was less than 0.02%. And we wanted to know what the drag, what the pulse inlet feed did. We got that nice plot there. So we wanted to know if dynamic layering from a reliable method for our final denticle model, and I think we can confirm, especially from this, the fact that it is less than 2% or less than 0.02%, that we can't use it. So in our future, we're going to implement FSI and then actually mesh and model the full denticle in our future work. But this was just a proof of concept model. That's my talk. Are there any questions?
Any questions?
Did you use the unified remeshing method, or did you just control the
I think differences between why we didn't use remeshing and why we used dynamic layering. So we didn't use remeshing at all.
Any other questions?
So as you look forward to bringing in your couple solid motion solver and everything, what are the material properties that you're looking at for the technicals? I don't know enough about that. Just to know what are you thinking along those lines?
So I haven't looked into the exact structural properties, but the main form of motion is right at the knuckle of the tentacle. So that's just going to be, that's a very, it doesn't have much torsional bending on the ankle there, but the actual structural, the structure of the tentacle itself is very stiff. So it's mostly just the rotating motion of the tentacle. So we'll just model that as a torsional spring, basically.
Thank you.
Any other question? We have 1 minute left. I have one quick question. Like when you were doing the modeling of your, you showed that there is 5% error in the
Yeah.
drag calculation. And what distance you were looking at, like a certain thing which was moving, if you make it bigger, that increases, or so this one, like that distance from the tentacle, that point where it shows, if you make that bigger circle, will it decrease?
We didn't do that, but the closer you make it, this is far enough away that it's 22%, but we didn't track it.
Moved it out.
This was far enough away, so we were fine.
So how much it is?